Good afternoon. My name's Elizabeth Baker-Keffer, and I'm Vice President of the Atlantic, and I wanted to welcome you to the 4 o'clock hour session in the Design and Sustainability track. This session is called How Will We Drill for Oil? A very timely topic given what's happened in the Gulf recently, and I know many of us have had questions about how oil is drilled offshore, why it's done, what safety precautions have happened, and I want to thank our underwriter, Shell, who's here with us this year for a second time, for volunteering just a few weeks before this to bring a couple experts to the Aspen Ideas Festival to talk about drilling for oil offshore and to answer your questions. So we're delighted to have two experts with us from Shell, John Hollowell, who's EVP of Deepwater for Shell Upstream America. John is responsible for all offshore oil and gas operations in the Western Hemisphere. And then second, Joe Leimkuhler, who will be today's primary presenter. Joe is Offshore Well Delivery Manager for Shell Upstream America, and his prior roles with Shell have included Subsea Development Manager for the Gulf of Mexico and Deepwater Drilling Superintendent. Joe is a member of the Society of Petroleum Engineers. He's part of the Petroleum Engineering Advisory Board at two universities, the University of Wyoming and Montana, and he's also chair of the Gulf of Mexico Deepwater Technical Symposium and the past president of the American Association of Drilling Engineers. So these two have deep expertise in the area that we'll be covering. They are both based in New Orleans for Shell, and we're delighted to have them here and have this open session for you all. Thank you very much.
Thank you, Elizabeth, and good afternoon, ladies and gentlemen. This is my first time to come to the Aspen Festival, and I must say I find it extremely interesting, and I'll be back next year. One of the reasons why I think it's so fascinating is the sharing of ideas. And in my business, the deep water business at Shell, that is critical to our success. Without the sharing of ideas each and every day, we can't handle and tackle the tough tasks that we have in the deep water business that we run. Now, we all know that the Deepwater Horizon represents a tremendous human tragedy and an environmental disaster. There's no debate. And out of that disaster, there has come many questions, one of which, can we drill wells offshore safely? And so today, what we want to try to do is show you how we drill wells offshore in Shell, do it in a way that we think is safe and responsible, and we've been doing it for quite a while. We're lucky to have Joe Leimkuhler. The good news here is you don't have to hear that from me. You get to hear it from a real expert, Joe Leimkuhler. And Elizabeth already introduced him, but Joe has been drilling deep water wells in the Gulf of Mexico for the past 23 years. And he is one of the deeper experts that we have at Shell in this area. So what we want to try to do today is show you how we drill the wells and the steps that we take along the way to make sure we do those in a safe and responsible manner. And after it's over, we hope to answer your questions you may have. So I want to leave plenty of time for Joe to explain and talk about the way we drill deep water wells. So with that, Joe, I'll turn it over to you.
All right. Well, thank you, John. It's a pleasure to be here today. It's also my first time here at Aspen. And I was, to be honest, I was a little bit nervous when I realized that it's 4 o'clock Friday, 1 hour away from happy hour. And I'm going to look at people who get to spend with an engineer in a PowerPoint presentation. So I'm quite pleased to see the number of you who are taking interest in the subject. So I was asked to kind of give an overview, kind of a high level. And Joe, you only have 20 minutes. Okay, got it. To walk you through what it is we do in deep water and how we do it. So to get right into it, we'll provide an overview of it. Obviously, as John mentioned, all the eyes are on the Macondo well blowout and the subsequent oil spill in the Gulf of Mexico. What happened downhole that actually led to it is still unknown, but we've learned quite a bit from what's been disclosed. And we've been able to formulate, there's two possible paths that were breached for it to happen. And we'll show you what that looks like on a wellbore diagram. But the day the well blew out, it's one of those days you will not forget. And it's certainly a defining moment for anyone whose career is in deep water drilling. When I went into the office and we learned that, yes, there's been a drastic explosion offshore in the Gulf that night, and there are people missing. And then you gather up your superintendents, and then you say, okay, how are we going to respond to this? We have our own people out there who are engaged in very similar wells, and we need to make sure that our operations are 100% safe. And one of your superintendents has just got a little bit of a glazed look in his eye, and you say, Wayne, what is it? And he says, well, my nephew's on there, and he's still missing. And it dawns on you that you work in an industry that is highly specialized, and it is a very small community, and everything is connected. And throughout the day, you learn more and more people that you know who were in that accident, who were injured. And then some of your coworkers, they're actually among the deceased. Coworkers you work with, their coworkers are among the deceased. So it's a very tight, small community that operates the rigs that drill for deep water in the world.
He was found though, right?
Yes, Wayne's nephew was indeed among the found, but it was 12 hours later, so a stressful 12 hours. So in spite of that, we have to deal with some of the realities that the energy that we require right now in our current energy mix for now and in the near term, it's debatable. It's one of the great questions of this conference, is how long will that remain a dominant energy source in our energy strategy? But for now and for the near future, it is certainly a key component of it. And it's important, I think, that as we engage in a conversation, everyone has at least a fundamental knowledge. So that's one of the things I hope to impart to you today. So a brief description of deep water in the Gulf of Mexico. A lot of people have different definitions of it. For us at Shell, it's roughly greater than 1,000 feet of water, or where the structure you're drilling from is no longer a fixed leg platform with its legs on the seafloor. It floats. So for most people, that's the defining point. Ultra deep water is about 5,000 feet of water or deeper. What you're looking at here is a diagram, and it's coded by water depth. So everything in blue and red is in greater than 5,000 feet of water. So you can see there's quite a bit of discoveries out there in excess of 5,000 feet of water. And the things that have a star on it, those are the operations that my crew runs in various major platform hubs across the Gulf of Mexico. And our latest hub is here. It's called Perdido. It sits in 8,000 feet of water, and we will directionally drill wells into 10,000 feet of water depths. So that is the deepest producing structure in the world and the deepest structure with a drill rig on it in the world. So it's significant in the sense that the Gulf of Mexico still counts for 30% of the U.S. oil production, and it's growing predominantly because of deep water, with a 33% increase since 2008. Globally, production from deep water doubles every 3 years, and it has tripled since the year 2000. And most of the Gulf of Mexico production increase is from the deep water fields. The production is prolific relative to what you get from other wells. The average oil well in the United States produces 10 barrels a day. The average offshore deep water well produces somewhere thousands of barrels a day. Highest producers, 42,000 barrels a day on the Shell Ursa TLP. So it is a tremendous resource, and it's something of huge magnitude and importance that's going to stay for a while. So the deep water drilling rigs and platforms, there's essentially 3 types that we use. What you're looking at here is a drill ship, and it truly is a ship, and it has a rig mounted on it. Other types that we use, and this was the type that the Macondo was what's called a semi-submersible. And it's usually a rectangular or a square-shaped rig with the hulls and pontoons down below. Both of these obviously float on the water. And both of them are typically what we call dynamically positioned, which means there's no mooring system associated with them. The third major feature we have is the actual deep water platforms, and this constitutes the bulk of the business that I and my crew manage. So in these platforms, you have both production and drilling ongoing at the same time. So there's multiple slots. We have platforms that have as many as 28 wells that are tied back to the platform. We'll be producing out of 27 and drilling on one of them, or working the rig on one of the slots. And add it all together, each of these components, they have to have all 4 common capabilities. First thing is station keeping. Obviously, it has to stay put. So if it's floating around, there's a certain watch circle that it can stay within. If it goes beyond that, then you have to suspend your drilling operations. So you have either a mooring system that you'll deploy, and we'll look at what a mooring system on one of these systems looks like in a minute, semi-imposed over the city of New Orleans, or dynamically positioned. So you have thrusters, you have propellers that link up to satellites in space, to acoustic beacons on the seafloor, so that you have 2 means of maintaining positioning, and it runs 24/7 through all currents, all weather activities, maintaining that rig within that watch circle so we can continue the drilling operations. The next thing you need is a riser system, and we'll take a look at one of those in a minute. It's a long tube that connects the rig down to the wellhead on the seafloor. Actually allows you to transmit your drill, transmit all your drilling fluids, and then also maintain control of the well while you drill. A wellhead system, which is the starter head on the seafloor, that's what you're going to hang all of your wellbore components off of. We'll show you how that's done. And then the rig itself, that's what you see on the news. That's what you see. It holds the drill pipe, pumps all the drilling fluids, and processes everything that's required to drill the well itself. So moving forward, for the deepwater floating platforms, to give you some idea of the scale of these, They're rather massive. They typically employ about 150 people out there at any one time. They work 14 days on, 14 days off, so there's 300 people directly employed on each one of these producing platforms. The scope is rather amazing. This is the city of New Orleans. So for those of you who have been to New Orleans, the tallest building in town is One Shell Square, the Shell building. It's 700 feet tall, 52 stories. And this is the auger TOP imposed over it with its lateral mooring system. And you'll notice the mooring system extends all the way from the shores of Lake Pontchartrain, across the river to the West Bank, to East New Orleans, over into the Garden District. It basically encompasses all of Metro New Orleans. These are huge systems. And what we're able to do from each of these sites is we're able to directionally drill and actually access hydrocarbon reserves in the earth that extend well beyond this. So this is the next slide is a diagram of the last well that we completed. This is off the Auger Tension Leg platform. It's the 16th well slot. Notice it says sidetrack 3, which means this is the third time we have drilled a well from this slot on the seafloor. And notice that if you were to position the rig directly over One Shell Square, whoops, wrong button. If you were to position the rig directly over One Shell Square, right here, and then start drilling, and you got on the St. Charles streetcar line, for those of you who have been in New Orleans, and you went through the Garden District, you went past Tulane, past the zoo, to the end of the streetcar line. And let me see if I can get this off of there without. Uh-oh. An engineer with a PowerPoint is really dangerous. Huh? Ah. When in doubt, go over to the computer. Okay. Thank you. Okay. Okay, so you're on the streetcar line, all right? You've come to the end of the line, and let me find the pointer again. And now you've gone to the end of the streetcar line, continue on for another mile, and there's total depth. It is 6 miles total depth. That's along the wellbore. The vertical depth was 27,000 feet, and our target is a 100 and 150-foot box that we were asked to hit. Okay, and it turned out to be a great well. It's a major discovery for us. But just the amount of technology it takes to do that is incredible when you look at what we use and what we deploy. So that's an idea of the scope that you have. And one of the things that you have to get your mind around in deep water is from that one site, we can explore virtually 6 miles in any direction, all the way down to depths of 28 to 30,000 feet. The next rig that we will deploy into the deep water Gulf of Mexico from a production platform will be the biggest in the world. It'll be able to handle 35,000 feet of drill pipe and drilled upwards of 40,000 feet of depth. So the capabilities truly are remarkable. So moving forward, how do you drill a well? So here we are in 5,000 feet of water. I've got a rig that I'm going to bring on location. And depending upon its system, I may run anchors, like you just saw in the prior picture, or we may set some beacons here on the seafloor, and we'll have transponders that, using acoustics, keep that rig on position, along with acoustics up to GPS satellites in space. So we'll get our position set up, and then the next step is I have to install my drive or my jet pipe. So we're going to start out with a pipe that's 36 inches in diameter, 3 feet across, about 3/4 of an inch thick in steel, extremely heavy. I'll put together about 300 feet of that. I'll attach it to drill pipe, and I'll run it down to the seafloor. And I'll ease it into the seafloor. I'll jet it down. It usually goes about 150 feet just by its own weight. We have a drill bit attached to the end of it inside the 36-inch pipe. We'll turn it on, and we'll basically jet that pipe in. And what that does is it stops the hole from caving in on me. If you've ever gone to the beach, dig down, right? When you hit water, what happens? Everything caves in because the sand grains are no longer touching. The water is supporting them. So to stop the hole and get my structural integrity to start the well, I'll put in 300 feet of jet pipe. The next thing is we'll actually start drilling with no riser. So all I have running from the rig all the way down to the seafloor is just drill pipe. And I'll pump seawater inside the drill pipe. So I'll drill with seawater for my first 2 sections. I drill with nothing but seawater, and I'll usually go about 3,000 feet down below the surface of the ocean. And I'll run 2 strings of pipe. After I get the hole drilled, I'll fill it up full of mud, full of clay. And that clay helps keep the hole open so it doesn't cave in on me. In time to get my pipe installed. Once I get the pipe down, I'll pump cement in, and I'll cement that pipe from the bottom of the well at that point all the way to the seafloor. And you've all seen the ROV pictures from the Macondo incident. That gives you a level of the clarity and how we can monitor things. So as soon as that fluid switches over and I see cement on the seafloor, we stop pumping cement, switch over to water, displace water all the way down to the bottom of the hole. So that's how we cement them in. The next step is I'll run my riser and my BOPs. And most of you have probably seen pictures of the riser that's installed. We don't run it that fast, okay? That was 24 hours of operations, okay? Takes about 24 hours to run 5,000 feet of pipe. So we'll latch the BOPs, blowout preventers, onto the wellhead on the seafloor, and now we'll test the BOPs, make sure that everything tests to the maximum pressure we expect to encounter on the well, because ideally we like the BOPs to stay down until all the operations are complete on the well. Connect the well to the rig, and now we'll resume drilling and drill ahead. So when it's all said and done, this is what I have. The one thing I like to describe a well as, it's an upside-down car antenna. So when your car antenna, for those of you who have the remote ones, it's got various sections in it, and it telescopes up. Well, in this case, a rig telescopes down. You'll start out with quite large pipe. We'll start off with 36-inch pipe, as I mentioned. And depending upon the area you're drilling, how fast does the pressure rise in your formations? As that pressure rises, at times I have to stop and run another string of pipe in the hole. So here, if the pressure rises higher than the rock strength here, I have to stop and run another string of steel casing. So I'll run these casings one inside the other all the way down to TD. And typically in deep water, it's not unusual to start out with 36-inch hole, and you're going to end up with a 7-inch hole. You're going to produce the well through a 7-inch casing. So that's what it takes. And one of the things I'm often asked is, well, what stops the water or the oil or gas from flowing out of the well while you drill? And it's nothing more than balancing pressures. So this is, in your reservoir, you have sand grains. And at any point in your reservoir, the rock, there's only two things that support everything above you. It's got to hold it all up. That's the sand grains that are in the rock and how much stress is between those. And whatever they don't carry, the fluid has to carry the rest. So fluid pressure carries the rest. So the way you maintain that and keep it balanced is, as it tries to get out, I'm going to overbalance it with pressure from my mud. So it's hydrostatic pressure. You go swimming in a pool, you feel the pressure on your ears. We'll run fluids that have at least twice that density. So for every depth you go down, it's going to be twice as much pressure as applied by water. So that's how we maintain our primary control, and we ensure that the well does not get away from us. So here we are at the end of the day. No, I don't think I want my update right now. If you like it, we can bring the screen back up when we're done if you really want the offer, but okay. So here you are at the end at the end, and your well's fully drilled. And now you're coming to one of the critical steps. And this is where they were at the Macondo well. You now have to transition from a drilling process and secure that well so you can abandon it and come back later with all the production equipment to produce the oil and the gas. So it's a very critical point. So the question is, how was your well designed? And this is where the concept of barriers and controls come into. Most people feel that the BOP is a barrier, that blowout preventer. It didn't work right on this well, obviously. We don't understand why yet. We will once that stack is recovered. But people think that is indeed a barrier, when in reality, the way to properly think about it, it's not. It is a control. Your barriers are actually inside your well. So in a barrier, barriers are inherent in your well design. So if you take a look at your well, here's your telescoping well here. Here's the last open hole I have. My hydrocarbon zone, my oil zone's down here. I've pumped cement down into the well. I've got check valves at the very bottom of the well to stop it from flowing back up the pipe I just ran in the hole. But there's another path it can come. It can actually come up behind this pipe in the clearance between all the other pipes I have run. Do I have barriers installed? If you run your last casing string as what we call a liner, which means I'm only going to line that last little bit of the hole, if I do that, I can install barriers, and we do that in our designs. So we'll have barriers set here, then I'll run another string of pipe, tie it back up to here with cement. So there's additional barriers all along my path. And the control is what I use is if my barriers fail and my fluids start to flow before production. is desired. So the BoP is actually a control. It's not a barrier. And we design our wells so that we rely upon our barriers, so we do not have to use our BoPs. That's our best practice, is design your well so you don't even need to rely upon your BoPs for well control. In 27 years I've been drilling in the Gulf of Mexico, I've never had to use my shear rams. So I'm very confident in the design. So you've got barriers on the inside of the well, you have barriers outside of the well that you have in place before you do the disconnection and you remove the riser and expose the well back to seawater. Are all of your barriers in place? So what you're looking at here is a contrast between two systems. The typical design that we use at Shell, which is to install a production liner. So there's my liner, I'll install that. Here's the two flow paths that oil can take after I install my liner. If it comes up the outside of it, I've got seals associated with my tieback. I've got cement that I'll place on top of it when I run the next piece to connect up. And I'll have a seal assembly up here at the mud line that is locked in place when I run it. So I have three barriers. On the outside, I've got three barriers on the inside. My cement plugs, when I run the tieback from the liner from here up to the mud line, I'll put additional barriers in here before I displace the seawater. And this is the case they had on the Macondo well at the time of the blowout. They relied upon the cement at the bottom to seal. There was a total path all the way up to the seal up here. The seal at the mud line was locked to the casing hanger. It was not locked to the wellhead. Could pressures build up high enough to lift the whole thing up? Do the calculations, and it is a possibility. Not saying it happened, but it is a possibility. On the inside of the well, the next step was to set these barriers you see here, set them here, and then install your lockdown sleeve up here. So it's a combination of exposure in your wellbore and did you have your barriers in place? And quite honestly, if they had to do it again, I think it would be done differently and the barriers would be in place prior to going to that step. So a BoP stack, how do they work? This is a BoP stack, a surface stack with all of the controls removed so you can see the elements. So you apply pressure out here to your rams, and this pressure closes your pipe rams. You have what's called a annular, which is a big bag, like a balloon. It'll seal on anything, it'll seal on nothing. And it's good for about 2,500 pounds of pressure. Then below that, you'll have your pipe rams, which clamp around the pipe. It allows you to circulate the well bore, and you'll come out some of your side valves on your stack, right here, and circulate heavy fluids into your well to get control of it again. And then in the end, you'll have your casing and your shear rams, and your casing and pipe rams that close on pipe. The goal is that make sure that your barriers are in place in your well so you don't have to use this for a well control event. Here's how shear rams work. The pipe itself is sheared. There's an accommodation space in the rams for the sheared pipe to go, and then there's seals here for when these two clamshell halves made up that gives you a pressure seal in the wellbore. So what tools are common to deep water and logistics? If you're drilling and you're way out, it could be up to a 20-hour boat ride. The supplies you need boats, and more boats. Every time I say boats, it's $35,000 a day. Helicopters, you're going to need your marine terminals, your ports. We have automated pipe handling systems. It's common in deep water rigs to have a fully robotic handling system. So unlike the movies where they're swinging the chain, getting all muddy, on a deep water rig, they sit in an air-conditioned cabin working their joystick. We employ state-of-the-art drilling systems. We can monitor everything while drilling. There's a computer system directly above the bit. There's a pulsing system that pulses all of that information up the hole. So within about 30 minutes of drilling a section, I know what it is, oil or gas. I know the rock type. I know the pressure. I know the acoustic velocity of sound in that rock to determine the porosity. And I can actually stop the drill bit and extend a probe out of the drill string and get a direct measurement of pressure. So it's truly state-of-the-art things that enable us to drill the well, which is why you see very rarely do you see the events you saw at Macondo occur while you're actually drilling. The risk is not that great in the drilling. It's actually in the transition phase. And then we have the subsea intervention capability. You've seen the ROVs that are giving you the pictures as you go onto the BP's website and look at the progress they're making. We also deploy real-time operating centers that have staff monitoring the wells 24/7. It's an extra set of eyes. It's also a great depository to document all of your data so that everything is available for us to analyze real time. And if there's data lost, problems on the rig, we have backup centers in Houston that immediately come in and pick it up. So in conclusion, the future of deep water is really safety. It all comes down to health, safety, and environment. It is our license to operate. And right now, at the present, we realize everyone is on the spotlight, whether you're BP or not. If you're out there in deep water, you are under the spotlight. So therefore, our focus has never, ever been greater on HSE. It's enabled by technology and operational performance. The total cost of the rig to run ranges from $1.1 million a day from a deepwater drill ship or a semi-submersible to $400,000 a day for a deepwater platform rig. And it's sustained by production. As I mentioned, the production rates in deep water tend to be prolific, especially relative to other wells that we drill in the United States. So that's where we are. Now it's time for Q&A. Did I do it in 20 minutes? All right.
Go ahead.
Oh, do they wait for the microphone and then I go ahead? Or? Oh, right there. Yeah.
Thank you for this briefing. Something that is difficult to understand from reading the news is who owns what and who leases what from whom, which is important to establish the chain of responsibility and the chain of command, which appears to have been very muddy in this case. Could you please help us to understand how the business runs, who owns what, etc.?
I can tell you how my business runs, absolutely. The rig itself is owned by the drilling contractor in most cases. On one of my rigs, Shell actually owns the rig. On the rig I showed you over New Orleans, we own that rig, and we pay a contractor to operate it for us. The well design is actually controlled by the operator, the oil company. The operational decisions on what is done is maintained by the operator. The how, the specifics of exactly how, it tends to be managed by the drilling contractor. Okay.
But it's got to be a kind of an integrated process, because as you drill the well, one of the key things that we have, and we leverage at Shell, we call it a safety case, which in essence is a true understanding of the risk from both the drilling contractor side about what could go wrong with that well and how do we mitigate that risk associated with that well, and our own Shell HSE, or health, safety, and environmental management systems. The two have to be integrated and linked so that everybody's on the same page about what goes on in that well and how we do it. But Joe said it right. The responsibility for the design of the well, Shell. Responsibility for what goes on how we're going to drill the well, Shell. The actual drilling and how the rig works, the drilling contractor. And for the type of floating rigs, Joe talked about platform rigs, which we do own. The floating rigs are all owned by contractors that we contract through to drill those wells. But the design and the basis for that design is a Shell basis.
And as John mentioned, it all comes together in the safety case. And it's something you're going to hear more of, because going forward, the new regulations require all deepwater operators to operate under a safety case, where your hazards are very well defined. Everyone understands what the major hazards are, what are the ways that hazard could get released, and then what are the barriers you have to stop it, and then the controls you have in place so it isn't. And it's under a safety case, whether you're the drilling contractor, or the operator, or even a service company out there, the expectation is you understand those high-level hazards, and you have the authority and the obligation to stop the job if you feel any of those barriers or controls are compromised. So after a while, working under a safety case, it almost becomes seamless because it's hard to tell who works for who.
Just a quick question. Can you just compare and contrast the well design you just took us through versus what was in the case of the BP well?
Sure. The other well on the side was the BP well. I don't know if that was clear. Let me go. I'll go back. All right. Okay, engineer animating too much. Okay. This is the Macondo well design. What's the yellow? Oh, the yellow is the drilling fluid that you have in the well. This is cement at the bottom, yes. Okay. Oh, sure. Point out the differences. So in a shell design, this difference here, we will actually have a full string of 13 5/8. Our last protective casing goes all the way to the seafloor. On this well, you'll notice there's liner segments all the way down. 16 inches, their last casing string they ran. And there are inherent weak points in the 16-inch casing. So if you got into trouble, as they have, and you need to get back on the well, and you need either A, pump heavy fluids into the well, hit it with higher pressures, you're limited by this well design.
Joe, point out the barriers again, because you said that, but I think to make sure people understand,
Sure.
the key difference between the two is the number of barriers in place.
Yep.
And actually the strength of the well, so to speak. So explain that to them.
So under our design protocol, you must have at least 2 independent verifiable barriers in place to any of the hydrocarbon paths in your well bore at all times once you run your production casing. So here, once I ran this casing, the oil could either escape up inside the well or escape up outside the well. In this case, you'll notice we have a barrier here at the top of the liner. We have cement placed inside the tieback string as well as outside. We'll have our P&A plug set up here. I'll have a seal assembly locked in place up here. So each one of these barriers you see I've coded in, I guess, pink. They are all barriers that you have in place outside the well bore. These are all barriers you have in place inside the well bore. And on the Macondo well, the barriers you have inside and outside is the cement at the bottom of the hole and your seal assembly up here on the surface. Question?
What does Shell do? Does Shell go beyond what the U.S. government requires in your drilling that some of the other companies might not?
Very good lead-in. Thank you very much. Okay. Everything you see here denoted by an asterisk is now required under the new regulations that have already come out since the incident. So you will have a seal assembly, and it will be locked in place to both the casing string you ran as well as your wellhead. You will have 2 independent barriers inside your casing as well as outside your casing, one of which must be mechanical barrier. You will not displace your well to seawater until you have all your barriers and things installed. And you will also operate your BoP stack such that while you're displacing all the drilling fluid to water, you will have no other operation ongoing on your rig other than that displacement, and you're measuring every barrel in and every barrel out.
We also drill our wells based on a global set of standards from Shell that is based on practices that we've employed across the world in drilling these type of wells. Often those global standards exceed the minimum standards required from regulators. 2, we have a very rigorous training and competency development program for our drilling engineers and drilling foremen. They actually get tested and have to pass tests in order to be deemed competent to drill these type of wells. 3rd is the robust design that we have, multi-barrier well design that is associated with the wells that we drill in the Gulf of Mexico and around the world for high pressure, high temperature type of wells, which is, these are one of them. The 4th one is the real-time operating center, which is really another set of eyes back at the beach. We've leveraged technology to help us have another set of eyes to watch what's going on with these wells, to see problems before they can occur. And the 5th one, and probably the most important one, is the HSE safety case. We employ the HSE safety case around the globe. We are the only operator in the Gulf of Mexico that currently employs this HSE safety case, which is one of the minimum requirements now being put out by the Department of Interior as we go forward. So those 5 things are critical, in my view, to help us ensure that we can drill a safe well, or give us the best chance to drill a safe well.
Question? Gentleman in the yellow shirt? Okay.
Can you describe the efforts that the industry made to bring help to BP in the case of the Macondo? Was there a lot of industry expertise?
No,
called
there
upon,
was.
offered?
Yeah, there was. I tell the folks inside of Shell this. BP's is a competitor of ours, a fierce competitor, and a partner of ours in the Gulf of Mexico. There's a time to compete, and there's a time to walk shoulder to shoulder. This is a time to walk shoulder to shoulder, and that's what we did. Immediately following the incident, we sent boats to the location because we have operations nearby where this was. Sent boats, sent helicopters. We have a sister rig, the Nautilus, that is the sister rig to the Deepwater Horizon. We sent an ROV with subsea intervention stab tools there to help. We also offered we have a deepwater training and development center in Robert, Louisiana, that also serves as our command center in the case of an incident, say a hurricane. We offered that to BP, and when you saw the media events it was from the Robert Training Center at Shell, and they had a command center set up in less than 12 hours for the incident. Now, you could go to every company in the Gulf of Mexico and they could quote things that we have done, and let me say we continue to do what we can as an industry to stop this leak. And that's not priority one right now.
Gentleman in the blue. Down here, he's had his hand up forever, and I finally saw him.
My question is, well, first off, I don't know whether you know, but the Court of Appeals turned down the moratorium on the Obama moratorium for drilling, and that was just today. But based upon what the moratorium was supposed to say, was that these two rigs were enough alike so that until they found out why there was a failure of the BP rig, that they would stop your drilling from happening.
Correct.
And what you're telling us is the contrary. Can you give us both sides of that argument?
Well, the analogy I would draw is when there's a plane crash, when a 737 crashes, until it's obvious why that 737 crashed, it's not unusual to see all 737s grounded. Do you ground all planes? No. So in my view, that until we fully understand what happened in this wellbore, what were the barriers that failed, do we also condemn other well plans? So in my view, I would fully support a moratorium where you will not run production long strings until we understand what happened. Can you continue to drill in deep water where you actually meet all the existing criteria that is in place? Certainly before, but definitely after the event, and you have a well design that is inherently different from this one, I think you should be allowed to continue. How old is the rig? I do not know. The well, what's a lifespan of a rig? A deep water rig like that probably has a lifespan of 15 to 20 years. And after that, it'll go through a modification phase. It'll be upgraded. It has to go in through its American Bureau of Shipping certifications. The Coast Guard highly regulates these vessels. So it's constantly inspected, constantly maintained, and once it reaches its usable life, it commonly comes into the shipyard for an upgrade. Next. Oh, the gentleman in the back with the hand way up north. Okay.
Hi. Thank you very much for coming. Given that the design of the well might have exacerbated the spill, could you talk a little bit about, as you understand it, what happened in the last 24 hours of the life of the Horizon, given that the well design was an acceptable well design, but that when you started needing 20 stabilizers and you only had 6, or you needed, you were failing your pressure test, your displacement tests, given that the well designs are different, but we've drilled a lot of those wells before. In the last 24 hours, as you understand it, what happened and why did they make, and I don't want you to speculate, but just what decisions were made that were really suspect there? Thank you.
The only thing I think you can comment on is it's something you're trying to resist speculation, because when you do incident investigations and you're trained to do incident investigations, the training is you don't draw any speculations or conclusions until you have all the data, all the facts. And it can actually be counterproductive to speculate because it can lead you down a path. And once you establish a position and you even advocate for a position, it's human nature to reluctantly back away from that. So we're coached and we're instructed and we're actually even required to avoid speculation until all the data is in. So all you can really state here is that prior to displacing this to water, did you have all your barriers in place? They were not. You can go through the prog, you can go look at the information, stuff that's out there. The next step, this very same plug set you see here, was to install that here. The seal assembly locked in place. The next step was to run a lockdown sleeve on top of this and lock the whole thing together. So were those done in the right sequence? Probably not. And that's about all we can say at this point.
It is important not to speculate, it really is. But at the same time, when these types of things happen, not necessarily a blowout, what we find in a major incident is that it's a cumulative effect of a number of things. And so I don't think you'll find one specific thing that occurred to create this. You will find a number of things, decisions that were made, decisions taken in the course of time that think of Swiss cheese lined up and all the holes lined up to have an incident. That's what will be the real learning of this and how we can improve on that.
The gentleman right here?
I think the most concerning event of all this is that nobody in the industry knew how to stop the blowout once it happened. And I'm sure if Shell or somebody knew, they would have called them up and said, just do ABC. So what have you learned and what are you doing in case there's another tragedy like this to not have it be such a tragedy?
Well, I think it begins with prevention. And prevention begins with robust well designs. So as we told you here, how we design a well. The more robust the well design is, the more options you have to intervene into the well in the event that something like that would happen. It's my belief that through more robust well design, you are significantly reducing the risk of an occurrence like what we saw, significantly reducing the occurrence. In the event that it did happen, though, Joe explained how we have deeper casing liners in the well back to the surface. That would allow you more options for intervention in the event that you had to do it. And so I think that the answer to your question is, and it's for me, it's through prevention, through robust well design. Will go a long way to reducing the risk linked to an incident like that.
Basically said that the Obama administration moratorium was wrong, and there was some speculation yesterday that the administration might put on another moratorium. And my question goes to how serious is this in terms of the industry and the economy of the Gulf? And as an expression of that, how many deep water rigs of the three kinds are or were currently working in the Gulf? And what is the worldwide inventory? How many do we have in West Africa and Brazil and so forth? And how transportable are these things, and how many have already transported to other areas, and what is the impact?
That's a lot of questions. So. I think let me say, I think your first question is the impact. Joe and I live in New Orleans, and rest assured we see and feel personally the impact of this each and every day. We've gone to where this has occurred. It's gut-wrenching to see how this has impacted, particularly the people that live along the coast. You know, New Orleans was recovering from a kick in the gut called Katrina. And I just moved back a year ago, and to be honest with you, between the Saints and some other things, the spirit in New Orleans has really improved a lot. You know, world champion New Orleans Saints, by the way. And who dat? And with that is really, you know, the devastation that was Katrina was beginning to be come back to life. And this is horrible for those people, horrible. Now that said, you ask what the impact of the moratoria is. Let me speak to it in Shell terms. We've got 4 of these drilling units, mobile offshore drilling units. 2 of them are currently idle. They're not working. So one of them is at a buoy in a shipyard near Pascagoula, and the other one is off location. 2 others are currently finishing up work that has been permitted, and after that, the amount of work that they'll have to do is very limited. Now, what can happen here is that these deep water rigs need to work, and there's plenty of places across the world where they can work. You talked about Africa, you talked about other areas of the world, and they will go there. Typically, when we contract one of these deep water drilling units, we do it for a very long period of time. So if they go out of the Gulf of Mexico, they won't come back. Good chance they won't come back anytime soon. So that's one impact. Another thing to think about, and I may have my ratios wrong, and Joe will correct me if I do, but for every person that works on a deep water rig, there's roughly 5 that support that person, whether it's supply boats, whether it's getting supplies to the distribution point to go offshore, restaurants, hotels. You start doing the domino effect of this. So 150 people at a time on the rig, 300 total times 5, you're going to get a picture of the impact that this has. This has impacted 33 rigs in the Gulf of Mexico between the various companies. And so it's a significant impact on our operations, as well as pace in terms of activity.
So to answer your other question, to my knowledge, from what I've seen in the press, 4 to 5 have already left the Gulf of Mexico. And when they leave, they enter into long-term contracts that typically run 4 to 5 years. So once the moratorium is lifted and we're able to come back, While those rigs are under long-term contracts, they will not come back. Question on the end?
How many wells are out there that are designed like BP versus Shell? Those two diagrams we saw.
I don't know. There have been some numbers that were put out in the Wall Street Journal that in some companies the number could be in the 30% range, some companies 14%. Shell was quoted as 8%. I've asked for what are those 8 wells? They provided us the information, and as it turns out, no, that they interpreted it wrong. We have 2 wells in the Gulf of Mexico that were drilled 6 years ago that are like that, but they were drilled in low pressure zones. And the 13 5/8 casing string that I showed you, let's see if I can get back there real quickly, it was strong enough so that no matter what happened in terms of any kind of seals that were lost or breached, that casing string itself was strong enough to withhold the full formation pressure. So this string of pipe right here, the 13 3/8 that you see going back, full string was run, but we had 13 3/8, and it was strong enough so that no matter what kicked it on the backside, with a lockdown sleeve here and the strength of that pipe, the well could handle a full hydrocarbon gas top to bottom in terms of load.
Our global drilling standards, though, for this type well would have been to run the production liner tieback string, as Joe showed you how to do it. That's our global standard for drilling that type well.
So, it depends upon the company. I can tell you for us, it's 2.
We've got to cut it off. We've got time for one more?
Okay.
One more.
One more. Okay.
We have another event in
Okay.
Would you hire engineers from BP at this point?
It would depend. You can't, when there's a failure that this occurs, until you understand the root cause, it would depend. I wouldn't condemn any one individual for an event that...
I would look at the capability and competence of that individual from a drilling engineering perspective. And if they come to Shell, they would drill wells according to our global standards and our processes and our practices. If they had the capability to do that, I think you would entertain that. But I think it's key to leave here knowing that we have a pretty stringent set of global standards, practices, and procedures that we use to drill these type wells. And if people demonstrate the capability and the competence to do that, then we can use them to do that. I don't know how that's hard. I'd be speculating to say how they do that. I know how Shell drills their wells. Thank you.